Hello. Good morning, students. Hello. Good morning, students. Hello. Hello. So, let's start our today's topic. So, it's okay. So, our today's topic. Today's topic is mostly based on electrochemistry. So that means we are mostly focused on the things like ionic activity, Debye-Huckel theorem, like this kind of topic in electrochemistry. Okay. So, uh, so let's start from our first assignment problem. Okay. So, let's start from the question number one. So question one. Question one is the ionic ionic strength of a solution of N by mixing aqueous solution of 23 level of 0.05 which is here to level of 0.05 and it is 0.25 ml of 0.04 ml CO2 and 25 ml of 0.01 glucose at a given temperature. So this is the problem, and the options are option A 0.03, option B 0.135, option C 0.075, option D 0.102. These are the four options given. Okay, so this is another question. The ionic strength. So these are the some four, one, two, three, four. So four solution of different molality and different volumes are given. So when these four solution to mixed with each other, then in the final solution you have to calculate the ionic strength. Okay, so at a given temperature. So these are the four options given. So before solving the problem, let me just discuss briefly how to calculate moles from the molarity. I hope you all of you should know this, but still I will just recall how to calculate How to calculate this number of moles for molarity. Okay. So the basic rule is this. So so molarity moles. Okay. So uh, moles is basically equal to molarity into volume. Okay. So let me just explain it with an example. So let's suppose um, let's take 10 grams of NaOH is mixed with 500 ml of water. Then what is the molarity? So for NaOH we know NaOH. So the molar mass of NaOH is, so molar mass is Na plus OH. So Na molar mass is 23 and OH. O has 60 and H has 1. So total molar mass was 40 gram per mole. Okay. Now in the problem only 10 grams of NaOH is mixed with 500 ml of water. So that means the mole is 40 gram equal to 1 mole. That means 10 gram will be equal to 10 by 40, right? So just read it clearly. 10 gram of NaOH equal to 10 by 40 equal to 0.25 moles, right? So now this 0.25 moles is mixed with 500 ml of water, but in the formula actually the volume should be written in liters actually, in liters. Okay, so 500 ml means 500 ml equal to 500 by 1000 equal to 0.5 liters. Okay, so the molarity will be simply just multiply these two things, 0.25 moles into 0.5 liters. This gives you basically 0.5 m. Let's take another example. So let's take I have a like 2.0 m stock of HCl. Okay, now I take 25 ml of this solution, this stock HCl solution, and dilute it to a final volume of 250 ml, right? Now what is the molarity of the diluted solution? Diluted solution. So basically what you have, you first prepare a 2m stock of HCl solution of 25 ml, and after that what you did here is mix this 2.5 stock HCl solution with 250 ml of final volume water. Okay, then what would be the molarity of the diluted solution? Okay, so in order to calculate this, what you have to do basically, so first what you have to do, this problem you have to solve in two steps. Okay, So first you have to calculate what is the number of moles of 2.0 m stock of HCl in 25 ml of solution. Okay. So first step 1. So moles of HCl in the initial solution. Okay. So moles would be simply, we already know, molarity into volume, right, in liters. So mole should be, molarity already know, it's 2.0 and volume is 25 ml, but we have to write it in liters, right? So 25 by 1000, this gives you basically 0.05 moles. Now in step 2, what you have to ask here is to find out that in the final diluted solution what should be the molarity. So in step 2, the moles you already know. Okay, now in step 2, molarity of the diluted solution. Okay. So molarity, molarity will be moles per volume, right? And volume you have to write in liters, right? In liters. Now molarity will be simply 0.05 moles by 250 by 1000. So if you calculate this, you will simply get 0.2 m. Okay. So in the final solution, the molarity of the HCl will be 0.2 m. Okay. So this is how you can calculate, like if molarity is given in a solution. So this is the formula. Using this you can calculate what is the number of moles that is present into the solution. Okay. So this is basically the formula. Okay. So these are basically two example. These two example I have basically shown how to like convert from molarity to moles and moles to molarity. Okay. And this is the formula actually. Moles equal to molarity into volume. Volume you have to write it in liters. Okay. And just we have to, but our main problem is we have to calculate the ionic strength of a solution, which is obtained by mixing aqueous solution of 20 ml of MgCl2, 30 ml of Na2SO4, 25 ml of LCNC, and 25 ml of glucose at a given temperature. Okay. So now, so now we have to ask to calculate the ionic strength. Okay. So let me first write what is the general formula of ionic strength. Okay. So because that's the thing we have to find out, right? So the general formula of ionic strength. Okay, so so this is the formula. I equal to half summation of I starts from I to n Ci Zi squared. So this is basically, I is basically the ionic strength. Okay. And Ci is basically, Ci is the concentration of concentration of ith component, because in the solution there can be many n number of components are there, right? So in order to calculate the ionic strength of the whole solution, you have to take into account of the ionic strength of all the components that are present in the solution. Okay, so Ci basically denotes the concentration of ith solution in molar units. So that units, you have to careful about the units of molar units. That means mole per liter. Z is basically Zi is basically charge of each ion. Charge of ith ion. Basically here Zi denotes the charge of ith ions. So example like for sulfate ion SO4 minus, the Z would be 2, because there is this is a cation of having two negative charges. Okay, so Z will be become 2. Okay, so but for multivariate atoms there will be, we have to use the like the much more combination of this Z. Okay. So this is it. This is the formula of ionic strength. Okay. So let me give you a small example how you can calculate this ionic strength. Okay. So example. So let's suppose calculate the strength of a potassium solution. So potassium chloride, that means KCl solution. Okay, so we have to basically calculate the ionic strength of a 3m potassium chloride solution. Okay. So in the solution, after the disassociation, the KCl will be disassociated into K plus Cl minus. So now here you have to calculate the ionic strength. So so as this 3m means so each component of this each ion has 3, so each ion has 3 mole of liter. This Cl minus also, this concentration of Cl minus also you have 3 mole per liter, right? So now as a result, each of the ion has 3 mole per liter concentration after the dissociation, right? And because of that, the ionic strength formula you can use half into Ci into Zi square. So this will be basically half into 3 into 1 square plus 3 into 1 square, because the charges on like K plus and Cl minus are both with plus 1 unit and minus 1 unit. So the Z would be 1 for both the cases. The charge is 1 unit, right? So here this should be simply half into 3 into 2. So I will be simply 3 unit. Okay. So this is how basically you have to solve the problem. Okay. So what is the things? So let me just write. Okay. So what are the things? So things to look out. So any kind of this type of problem, 3 main things that you have to like consider before solving any this type of problem. So first thing is identify all the ions. Okay. So like let's suppose NaCl is there, right? So basically this will give a Na plus Cl minus. Similarly, let's suppose MgCl3. So after the dissociation, it simply gives you MgCl2. Sorry, MgCl2. So this basically gives you Mg2 plus 2Cl minus. So there's two plus ions and one negative ions, right? So so you have to like first figure out what are the type of ions, what are the charges of the ion that is present in the solution. That is the first thing that you have to identify. Second thing is determine the concentration of each ion, right? This is also a very important thing. Okay, so let's suppose I have 1 m of MgCl2. Now in the solution, when it is dissociated, it basically gives you Mg2 plus and 2Cl minus. So what does that mean? That means that the concentration of Mg2 plus would be simply 1m, and the concentration of Cl, as there is a 2 in front of it, that means 1 MgCl2 I am basically dissociate into 1 Mg2 plus and 2 Cl minus. Okay, so MgCl2 is dissociated in 1 Mg2 plus and 2 Cl minus. That means each one molecule of MgCl2 is dissociated into 2 anions of Cl minus. Okay, so that means the concentration of Cl minus would be 2m. That means that the concentration would be twice of the MgCl2, right? So so this thing also you have to like look out when you are solving this kind of problem, like the concentration of each ion. And third is the charges. That I have already discussed. Okay. So determine the charges. So like charges. Okay. So like here MgCl2. So basically Mg2 plus and 2Cl minus. So basically here has 2 uh, plus 2 charges, and here you have just negative charges. Okay, so these things also you have to careful about. What is the charges after the dissociation? Charges of the ions. Okay, these three things you have to I mean careful about when you are solving this kind of problem. So after like discussing all these things, like how to calculate molarity and vice versa, and next thing is how to calculate ionic strength, and what are the things that you have to look out when you're solving this kind of problems. After discussing all of this, now we will solve our main problem. So our main problem consists four different solutions. Okay, so first what you have to do, as like these three solutions are mixed with these four solutions is mixed with each other. So first things you have to do, you have to convert the molarity into mole, right? These four things. First you have to convert the molarity. So step one. So now we are solving the actual problem. So actual answer. Solution. So this is the answer. Start from here. So first step one is calculate moles of each compound. So first is MgCl2, right? So MgCl2. So MgCl2 is how much? Is 20 ml of 0.05 m. Okay, so that means the moles in terms of mole, it should be 0.05 into 20 by 1000, right? So this will basically gives you, if you calculate zero cancel, and 0.5 into 2 basically 0.1, so this will gives you 0.001 moles. Similarly, option 2 was in what is so second solution is Na2SO4 30 ml of 0.05 m. So Na2SO4 Na2SO4, so that is basically 0.05 m into 30 by 1000. This will basically gives you 0.0015 moles, right? This will basically gives you 0.0015 moles. Third solution was, what was the third solution was? AlCl3, right? AlCl3, how much amount? AlCl3 was 25 ml of 0.04. Okay, so 0.04 into 25 by 1000. So this will basically gives you 0.001 moles. The fourth solution was glucose, but glucose was how much was glucose? So glucose was 25 ml of 0.01 m. So it will simply gives you 0.01 into 25 by 1000. So this will be 0.00025 moles, right? This is, I think, yeah, this is fine. And one more important thing about glucose is this is basically a neutral molecule, right? So it will simply, so that what does that means? That means that it will not convert into iron, right? I mean split into iron, right? Ion. So if it doesn't split into iron, so this actually means that it simply doesn't contribute to ionic strength. Right, because if it doesn't disintegrate into iron, so by common sense it simply doesn't make any contribution to the ionic strength of the solution, right? This is a bit straightforward. Now I've calculated the all the moles of each of the compound in its individual solution. Now what happens? Now we mix it, right? So after mixing, now we have to calculate, like after the mixing, you have to again calculate the concentration of each, okay, each ion, right? Like when you mix it with each other, so it will basically like mix it with each other, then it will like simply like split into ions. Now, so for each ion you have to calculate like its concentration in terms of molarity, right? So step 2 was calculate the concentration of each ion at mixing. Concentration of each ion after the mixing. Okay, so total volume was, so total volume is 25. So first let's start from 20, 30, 25, 24, right? So 20, 12, 20, 30, 25, 25. This is the total volume. Total volume of after mixing all of the solutions. So this will receive uh, 20, 20, so 50, 50. This will gives you 50, sorry, 50, 50 equal to 100 ml. So basically 0.1 liter. Because in order to calculate the molarity, we need the volume in terms of liter, right? So it's better to write it in terms of liter then, okay. So now for MgCl2, MgCl2, it will be simply gives Mg2 plus into 2Cl minus, right? So what is for Mg2 plus? Mg2 plus the concentration is 0.01 into by 0.1, right? So because now we are converting moles into molarity. So in terms of molarity, we already know this thing, right? Molarity will be moles by volume, right here. If moles equal to molarity into volume, so molarity will be moles by volume, right? So we are doing this here actually. So for Mg2 plus, it would be 0.01 m. Now Cl2, there is 2 moles of Cl2 per 1 mole of MgCl2. That means for Cl2 to be 2 into 0.001 by 0.1. So this will be basically 0.02 m of Cl2. Similarly, for Na2SO4, so for Na2SO4, this basically gives you 2 Na plus into SO4 2 minus, right? So for 2 Na plus, so that means it for 2 Na plus it should be for sodium it is 0.0015 moles. So that for each mole Na2SO4 there will be 2 moles of Na plus, right? So that means 2 into 0.0015 by 0.1. That basically gives you 0.03 m. And for SO4 2 minus, this basically gives you SO4 2 minus is you get 1 mole for Na2SO4, you get basically 1 mole of SO4 2 minus, right? So for SO4 2 minus, it should be simply 0.0015 by 0.1. So that basically gives you 0.015 m. So MgCl2 Na2SO4 we have already calculated. And in third was this. Third was AlCl3, right? AlCl3. So AlCl3 basically disintegrate into Al3 plus 3Cl minus, right? Now for each mole of AlCl3 there will be 1 mole of Al3 plus, right? So and AlCl3 was 0.01 moles, right? So for Al it should be 0.01 by 0.1. This should gives you 0.01 m. And for each mole of LCl there will be 3 moles of Cl minus, right? So that should be 3 into 0.01, sorry, 0.001 into 0.1. basically gives you 0.03 m. And we already discussed that the glucose will not simply disintegrate into any kind of ion, so there should be no contribution comes from the glucose level. So now we get all like all the ionic, all the moles and all the ionic strengths, everything we have calculated, right? So now the next thing we will be simply calculating the total ionic strength. Okay, so total ionic strength. So total ionic strength I will be already discussed, that is half into CI into ZI square. So I into half into, so let's first take so let's first take the MgCl. So MgCl2, the C was 0.1, 0.01, 0.01, and Zi square would be, Mg has two cations, right? Two units of iron, right? So 2 square. Second comes from the Cl minus. Cl minus has 0.02 m of concentration, 0.02, and it has the single anion, single unit of anion, right? So 1 square. Third things comes from the Na2SO4. So Na2 has 0.03, and there will be just one positive, one unit of positive cation. So next comes SO42 minus, it's simply 0. So SO24 minus has 0.015, 0.015 into, it has basically 2 units of anion, so 2 square plus AlCl3. Al has 0.001 moles, and it basically just have so Al has 0.01 m, and it has 3 units of cation, right? So 0.01 into 3 square, right? And last comes the Cl3 minus, Cl minus, right? 3 Cl minus. So Cl minus basically has 0.003 into, there is just single anion is there, so just 1 square. Okay. So these are basically all the contributions that comes for all the contribution that comes as an ionic strength in the solution. Total strength is this. So now we calculate it all of the things. So I will be simply half into 0.04 plus 0.02 plus 0.03 plus 0.06. Like if you calculate all these things, we will probably get all these results. So 0.06, now comes 0.09, last comes 0.03. Now half into, if you add all this 1, 2, 3, 4, 5, 6, you will be getting 0.27, and the final result will be 0.135 of I. So I 0.135 m. Okay, this is the result. Okay, so this is the the final solution after mixing all the 3 solutions. So basically this would be the ionic strength we will be getting. Okay, so let me just revise all of the things that I have done. So this was initially the problem. Okay, 20 ml of NaCl2, 30 ml of Na2SO4, 20 ml of LCl3, 25 ml of glucose. Okay. So first thing what we have done. So so basically the first step, we have calculate the moles of each compound, like before the mixing. Okay, the MgCl2 was 0.01, Na2SO4 is 0.015, AlCl3 is 0.01, and glucose is this. But for the glucose, as it's a neutral molecule, so it simply doesn't contribute anything into the strength of the solution, ionic strength of the solution. Then after the mixing, the total volume becomes this 100 ml. And in the after the mixing, we have to calculate the concentration of each ions, okay, each ion's concentration, and also have to from there also we have can also get the charges of each ion. Okay. So first to calculate the concentration for MgCl2, Na2SO4, AlClC, and after doing all of this, uh, this basically gives us the Ci into this equation, right? So, and also we need the Zi, that means the ions. I mean the units of the ions. Okay, so and we have to multiply those two Ci and Zi square and take the summation for each component, right? Simply we have done the same thing here, like we have multiplied the concentration and the square of the ion units, and we have add all of these things. And after doing that, this is basically the ionic strength we are getting. This is one result. Okay, so this is it. This is how we will solve this kind of problem. Okay, so I hope all of you understood how to solve this kind of problem. Okay, so this is the problem one. Okay, so now comes the problem 3. Yeah, so problem 2. So what is the problem 2? The problem 2 is the mean ionic activity coefficient of 0.05 solution of NO2SO4 at 25 degrees centigrade is given by option A 0.483, option B 0.679, option C is 0.536, and option D is 0.403. Okay. So now from here you have to basically find out what is the ionic activity coefficient. So now in order to solve this kind of problem, okay, so you have to basically know a theory. Okay, so a law basically, not a theory, it's a law basically. So this law is known as Debye-Tucker law. The short form is DHLL. So what is this DHLL? So let me just write it. So the DHLL is a fundamental equation that describes how the activity finish soon. It is gamma basically of ions in dilute solutions vary with ion strength. And one more important assumption that this law basically holds is it is particularly useful for low concentration of solutions. That means I should be less than 0.1 m. So this is basically the Debye-Hopper limiting law. So this is basically a fundamental equation in electrochemistry, describes how the activity coefficient, that is represented as gamma of ions, in dilute solution vary with ionic strength. That basically in the question itself we have to find out the mean ionic coefficient for aqueous solution and aqueous solution. So how this active coefficient has been calculated in a dilute solution, which is having a defined ionic strength. Okay, that has been determined by using this DHL, Debye-Hopper limiting law. And the main assumption behind this law is the solution should be in low concentration. Okay, so that the I should be like less than 0.1 m. Okay. I means the ionic activity should be less than 0.1 m. In that regime, it is basically useful of the, I mean, not exactly 0.1, but close to. Okay, so I is very close to 0.1. So so now what we are doing, so the problem is okay, so let me write the equation. Okay, so the equations according to this law, the equation is this: log gamma experience vector minus z plus z minus I. Okay, so so basically here so basically in this this is the equation basically, DHL equation. Here gamma plus minus is mean ionic activity coefficient. A is Debye upper constant. Z plus minus is charges of cation and anion. Okay. And I is the basically the ionic strength. Ionic strength of the solution. That expression you already know, right? I equal to simply half summation of Ci Zi squared. This is the ionic strength. So now the next thing that you have to calculate is the what is under the things you have to calculate is so for the Na2SO4, right, in the problem Na2SO4. Okay. So so how to do that? Okay, so so for Na2SO, sorry, Na2SO4, it will be simply disintegrate into 2Na plus SO4 is right. And so the concentration was 0.05 m. So that means the concentration of Na plus, if this is 0.05 m, the concentration Na2 plus would be simply 2 into 0.05 m, right? So this will gives you 0.1 m, right? And for SO4 minus, it gives you 0.05 m. Okay, so this is it. So now the charges, right? So this has +2 charges. Sorry, this has +1 charges. This is as -2 charges. So the ionic strength should be half into 0.1 into +1 square plus 0.05 into 2 square, right? So this basically gives you half into 0.01 plus 0.2, so 0.3 by 2 gives you 0.15. I will strength 0.15 m. So so basically just like how we have done in the previous problem, same procedure we are using here also. And by doing that, this is the ionic strength we are getting here. Okay, so now by using this formula, using this value of ionic strength, we have to calculate the ionic activity, right? So now what we have to do, so you already know this formula, right? With this formula, okay. So this formula is so log of gamma equal to minus a z plus z minus into total I. So now here simply taking the A value is, I have mentioned, right? A value is Debye-Hückel constant. So it basically has a constant value that I forgot to mention here actually. The value is 0.509. It's a constant value for water at 25 centigrade. So in this system, all of the things that you have calculated are in aqueous solution, right? So we can safely use this constant value for our calculation. So so here A is 0. So A is 0.509 plus 2 into 1, the charges basically. So 2 into 1 into Newton under I is this 0.1. Now if you calculate this log of gamma basically gives you uh, 0.509 into 2 into, if you calculate root of this gives you 0.387, and at the end you'll be getting 0.393 log of gamma. And from here gamma would be simply this log has 10 base, okay, so base 10, base 10, base 10. So 10 by 0.393, which will be approximately equal to 0.473. Not exactly, approximately, because like we have to equate the answer right here. The closest answer, it will be comes to this 403. Okay. So this is basically how you will be getting calculated. So so let me just explain it once again what I have done here. So so in the question so in the question you have been asked to find out the mean ionic activity coefficient of a 0.0 aqueous solution of NaCl at 25 degrees centigrade. These are the options are given. Now, in order to solve this type of problem, then we have to use a law which is known as d by Hopper law. So this law basically is a fundamental equation in electrochemistry that describes how the activity coefficient gamma of ion in dilute solution vary with ionic strength. And this is basically this is the equational form of the of this law, and this is basically applicable in like a very dilute solution. And there are also other assumption. Okay, like there is also another assumption that this this is only like this doesn't like consider like the charge, the sizes of the charges. Okay, this only consider charges as points. Okay. So if you want to consider a finite size of the charges, then this equational form simply doesn't work. For finite size charges, there is another form of the equation, but that we will not consider for this equation for this problem. Okay. We are considering the charges as a point charges. Like there is no finite size of the ions we are considering right now. Okay, so this will be the equation that we'll be simply using. So gamma is basically the ionic activity coefficient that we are going to calculate. A is a d by Hubble constant, which is a constant value at for water 25 degree. Z plus minus is the charges of cation anions, and I is the ionic strength. So first thing we are calculating the ionic strength. Na2SO4 would simply disintegrate to Na plus and SO4 to minus, and the concentration would be 2 into, because this is 0.05 mm per solution, right? So the concentration of Na plus would be 0.1 m and SO4 to minus 0.05 m. Now if you calculate the ionic strength, that would be 0.1 into 1 square, that is the charge here, and 0.05 into 2 square, that is the charge here. So that basically gives you this, and the total ionic strength will be 0.15 m. So you got the ionic strength. Z plus Z minus you already know, 1 is 2 and 1 is 1. Okay, so that you know, and A is the constant. So you have just substitute all of these values here, and after doing all the calculation, this is the gamma value. So after calculating all of this, the gamma value comes close to around 0.403, and this is the correct answer will be this 0.403. This is one problem that we're going to count right now. So this is the problem number 2. Okay, so now we come to the so problem 1 and 2 have discussed. Now we come to the problem 3. Okay, so problem 3. Okay, so okay. So problem, what is problem 3 basically telling us? So problem 3 is calcium, calcium boride, sorry, calcium carbonate, sorry. Calcium carbonate is heated in a closed container and the equation is CaCO3 is equal to CaO, that is this is solid, this is only solid, plus CO2 gas. So equilibrium is established. Now I have to calculate now we have to calculate the system has option A 3 phases and 2 independent components. Option B is 2 phases and 2 independent components. Option C is 2 phases and 3 independent components. Option D is 3 phases and 3 independent components. These are the 4 options that are given. So now let me just first write the equation. So this is the equation CaCO3 that is in solid is equal to disintegrated into CaO solid plus CO2 gas. Okay. So now first we have to identify the phases, right? So step 1. So basically you have to calculate a number of phase and number of independent components. Okay. First thing we have first identify the phase. Identify in the phases. Okay. So phase 1 is this CaCO3 solid phase, right? So phase 1 is so solid phase 1 is CaCO3 is a solid. Okay. Next is CaO is also a solid, right? So solid phase 2 is CaO is a solid, and Next is gas phase. There is only one gas phase, right? CO2 is a gas. So how many phases are there? One solid phase two, and gas phase. So total phase is 1 plus 1 plus 1 equal to 3. And this is the total 3 phases are there. Now we have to basically find out what are the distinct 2 phases are there. Okay, that basically gives the independent components. Independent components mean basically the two the distinct phases. So here are the 2 distinct phases. So independent components basically means the distinct phases exists in the system. For this system, the 2 distinct phases, gas plus solid, right? So here so here the 2 very distinct phases of gas and solid. So independent components C basically will be 1 plus 1, that is 2. So the answer should be 3 phases and 2 independent components. Okay. So option A, I think option A would be the correct answer. Option A is the correct answer. That is 3 phases and 2 independent components. Okay, fine. This is the problem 3. This is done. Question 5. Question 4 is this. So, so here the problem is the two component system which has both lower critical solution temperature and upper critical solution temperature is option A is water, phenol. Option is water, trial, triethylamine. Option C was water, nicotine. Option D was water, acetic. Water acetic acid. So, so, so this question is basically, in order to solve this question, we need an understanding of the phase behavior of the two component system. Okay. Specifically, the things that you have to focus is on the critical solution temperature, right? So before like concluding anything, so few concepts we need to know, right, in order to get the correct answer. Okay. So let me write those things actually. So first thing is like one thing is called miscibility. So what is miscibility? So when two liquids are mixed, okay, so either they completely dissolve with each other, or they can form two separate layers, right? So so when like two mix with each other, it will be called miscible, and if it's form two separate layers, it's simply called immiscible. Immiscible fluid, okay. Immiscible liquid, okay. So, and this also depends on the temperature, okay. So, this is for fixed temperature, okay. We're considering two separate cases. So, when two liquids are mixed, when they are like mixed with each other completely, then it's called miscible. These two liquids are miscible. If it's not mixed, then it's called immiscible. Next thing is called critical solution temperature. Okay. So this is basically uh, a temperature where a mixture when a mixture when a mixture of two liquids becomes miscible, or conversely, a mixture that is already miscible starts to separate into two phases. So this can be done upon by both by heating or cooling. Okay. By doing heating or cooling, in either way, if you able to sustain that critical solution temperature, So it will simply do two kind of tasks. Either it can make two liquids become miscible with each other, or conversely, in a mixture it can also make that mixture separate into two different phases. Okay. So this is called a critical solution temperature. Third thing is upper critical solution temperature. What is this? So this is like the critical temperature. This is basically the critical temperature above which two liquids are completely miscible in all proportions. Okay, so basically in a mixture, if you cool down the mixture below this upper critical solution temperature, this will basically result into a phase separation between these two, these two liquids. Okay, so this is called the upper critical solution temperature. Similarly, there is another concept called lower critical solution temperature. So what does this mean? This means this is the critical temperature below which liquids are completely miscible in all proportions. So so this is kind of opposite of upper critical solution temperature. So basically, if you heat a mixture above this lower critical solution temperature, then the mixture will basically phase separate. Okay. So it will basically cross that lower temperature, cross the critical solution temperature, and the system will basically phase separate. So upper solution temperature and lower critical solution temperature, both you have like understood. Okay. So so like now so after explaining all of these things, now we are basically come back to our main problem. So so our main problem was, out of all of these four solutions, which has both lower critical solution temperature and also upper critical solution temperature. So so let me write each of the solutions separately. From there itself we can easily calculate. So first is water phenol. So what is water? Water phenol basically has a high temperature, right? Water and at high temperature, what happened? Phenol and water both are miscible with each other. Okay. So what happened, as you decrease the temperature, they like become partially miscible, and eventually, if you increase the temperature more, then it will basically separate into two phases, right? So that means you are cooling the water phenol solution and after a critical temperature, these two miscible fluids become completely phase separate. That means you're cooling the thing, and that means only the upper solution critical temperature exists for this solution, right? So at high temperature, just write it as T at high T. Okay. Phenol and water are miscible, and at lower T they become phase separate. Okay. So this simply implies that this system only has, let's call it as UCST, and this call it as LCST. Lower solution, lower critical and upper critical. Only has UCST, right? Upper critical solution. Okay. Now the second was water trimethylamine. So water trimethylamine. So in water trimethylene solution, what typically happens that, so at low temperature, what happens is water and trimethylamine are miscible. But as you increase the temperature, they become partially miscible, and if you raise it more, it will eventually phase separate. So what does that mean? That means it only has lower critical solution temperature, right? Only in this kind of system, only when you heat the system, in that case only it will phase separate. So it only consists lower critical solution temperature. Okay, so let me write it. So at low temperature, water and is miscible, but as T increases, they become partially miscible and eventually miscible. So this system only has LCS, that means lower critical solution temperature. So we have to discuss both water phenol and water triethylamine from us answer. So next comes water now the third option is come water nicotine. Now this is important because water nicotine temperature, in water nicotine solution, at intermediate temperature only, this water and nicotine are completely miscible with each other. This is only at a temperature, intermediate temperature rate. However, if you either increase or decrease the temperature, from this intermediate range, this mixture will simply will phase separate into two different phases, right? So this actually explains that this water nicotine solution basically has both lower critical solution temperature and also upper critical solution temperature, because these two only miscible at an intermediate range, right? So whether you are cooling it or heating it, it will, if it simply deviate from that range, it will simply phase separate into two different liquids, right? So that means it has both UCST and also LCST, right? So let me write this thing. So at right, meters, integrate, temperatures, water, and liquid, time, and accessible. However, if one another increase or decrease the temperature from the intermediate range, what happens? It will simply the mixture will simply phase separate, right? So that means both UCST and LCST exist for this water nicotine, right? So this is the thing, 1, 2, 3. Now comes the option 4. But I don't think we don't have to check the option 4, right? You already get the correct answer, that is water and nicotine, right? So the correct option is the water nicotine, option C. Okay. So this is it. The problem number 4 we have done. Now comes to the very last problem. So problem number 5. So problem number 5. So consider and consider degree molar mixture of water that has a boiling point of 100 degrees centigrade and downline boiling point of 110 degrees centigrade, and there are some facts are given. I'll write it. So what is not true? So what from those facts, what are not true? What is not true? The option is the system will constant temperature till it's exhausted in the liquid phase. Option B, boiling point of the mixture is and of water. Option C, the vapor will instant composition till one of the component gets exhausted. And option is the boiling point will be 100 degrees centigrade and 100 degrees centigrade. So there are basically very big statements are given here. So so two equimolar, that means both have the component of the mixtures having the equal amount of equal amount of mole, and they basically form an immiscible mixture of water and toluene. So water and toluene are the two components of the mixture, and their boiling points are given 100 degree for toluene is 100 degree. And from these four statements that are mentioned here, you have to find out what is not true. So how can you do this? So before doing that, let me write just some of the things that actually you already know, but still I'm writing. So immiscible. So what does immiscible means? When two liquids are immiscible, what does that mean? That means that they form separate layer and do not mix with each other. Right? This is basically the meaning of immiscible mixture, right? So this is immiscible fluid liquids. Next come the vapor pressure. So because in this problem also this vapor pressure because in the statement also you can see there is vapor thing is there. So we have to like consider what is the vapor pressure means. Okay. So what happens is that in a fluid mixture of fluids, okay. So each of the liquids in the mixture has its own independent vapor pressure. Okay. That is independent with each other. Like in this case, but this is only true in case of immiscible mixture. Okay. Like in the immiscible mixture, like two two liquids has their own independent vapor pressure. So let me just write here. Vapor pressure. So the immiscible mixture, each liquid has its independent each liquid has its independent vapor pressure. Vapor pressure. This is the vapor pressure. Next is the boiling point of the mixture. This is also important thing, right? In case of in case of immiscible mixture, boiling, the concept of boiling point is also very important. So, so in the mixture, what happens? We know that simply a solid when at a boiling temperature, what is the condition of pressure that has to satisfy by a liquid when it comes to a boiling temperature and it start boils? Basically, the pressure of the liquid should be equal to its to the atmospheric pressure, right? If the pressure meets this condition, then only after reaching the boiling point, the liquid will start to boil, right? So simply here also, in this case, like this two liquids are since immiscible with each other. So what happens? Uh, so in the boiling point, so so boiling point simply means the total vapor pressure that means the that means basically the sum of the vapor pressure of each component should equals to the atmospheric pressure. This is very important criteria that this liquid has to satisfy. Otherwise, it will not boil. Simply not boil. Now, we are checking the analysis. We will simply do the analysis of each statement. So let's check the statement one. Okay. So I just write it in place. Okay. So analysis of the statements. Basically, we have to find out which is not true. That means false. Out of these four given statements. So statement one, what it basically tells us, the system boils at a constant temperature till one of the component is exhausted in the liquid phase. So since the components, so since it's an immiscible fluid, so the components of this fluids are components in this mixture. Each fluid in the mixture is independent, right? So vapor pressures are also like the vapor pressures are also like vapor pressure also dependent on the temperature, right? So the vapor pressure of each component will also also determined by the temperature, right? That is also independently happening. So so the mixture will only boil when the sum of the vapor pressure is equal to the atmospheric pressure, that we already know. And since as the component boils off, as one of the components boils off, the temperature remains constant until one of the component is exhausted, right? So you like so at a constant temperature, so what happens like if suppose the vapor pressure is like constant with the atmospheric pressure for that temperature for one of the component, okay? So for that temperature only that component will boil off, and this will simply happen until and unless that component will be exhausted. Meanwhile, the other component will be fixed into the system. Okay. So the statement one is like so let's write. So for statement one, statement as the component values of the temperature remains constant, right? Until one of the component is exhausted. This is the statement one. So that means this option statement one is true, right? This is true. Now comes the statement two. So what statement two basically tells? So statement two tells us that boiling point of the mixture will not be less than that of a water. Okay, let's check this statement. So the mixture, we know that mixture will only boil when the sum of the vapor pressure of both the components, I mean both water and toluene equals to the atmospheric pressure. But what happens, since we know that toluene is less volatile than the water, right? So that is the reason it has a high boiling point, right? Here you can see high boiling point, that means less volatile than the water. So that means it will boil at a at a higher boiling temperature than the water. Yeah. So that means its vapor pressure at a given temperature will be lower than the water's, right? So as it's like to reach that so the vapor pressure that is required for toluene, okay, for boil should be less than than the water, right? And to reach that atmospheric pressure, the temperature will be higher than the boil. So definitely, so to make that vapor pressure equal to the atmospheric pressure, the temperature should be higher than the boiling point of the water, right? Otherwise, it will uh, not simply boil, right? The whole mixture. So that means the boiling point of the mixture is less than the water is not true, right? So, so let me just write. So, since the since union has boiling point its vapor pressure at a given temperature should be less than water, right? This simply means to reach the atmospheric pressure, the temperature of the mixture need to be higher than 100 degrees centigrade. So this is basically common sense, right? So so this statement basically false. So statement number 2 is false. Let's check the other statements also. So statement 3. Statement 3. So statement 3. So what statement 3 tells us? So statement 3 is here. So here what is telling that the vapor will have a constant composition till one of the components gets exhausted. Uh, the vapor will have a constant composition till one of the components get exhausted. So what happens here? Uh, so we already discussed, right? Since each component boils independently, this, since this is the immiscible fluid, right? So two liquids are phase separate with each other. So two liquid in the mixture, two liquid can boils independently because they're independent to each other, right? So so the vapor composition, the vapor composition will reflect the ratio of the vapor pressure of the two components of the boiling temperature. So this is so vapor no. So at a given boiling temperature, so at a constant temperature, if as the boiling continues, this ratio, that means the vapor composition, I mean the ratio means also means the vapor composition also will remain constant until one component is exhausted, right? So so at a particular boiling temperature, so that means the vapor will have a constant composition, right? Because these two components are independent with each other, right? So let me just write the statement 3 of the result. So since each component boils independently, the vapor composition will reflect the ratio of vapor pressure. Vapor pressures of the components at the boiling temperature. So this means that as the boiling content is at a constant temperature, definitely the ratio as well as the vapor composition will remain constant, right? Since until one component is getting exhausted. So as the boiling continues, the ratio and hence the composition will remain constant until one component is exhausted, right? So this means that statement 3 is also true. Statement 3 is also okay, fine. So statement 1 and 3 we have found true, but statement 2 is we find as false. Now comes statement 4. Now statement 4. So in the statement 4, what it states, so statement 4 is the boiling point will be 100 and 110 degrees centigrade. So between will be between, sorry, between. So okay. But this in the statement 2, we have already discussed that at a boiling temperature of 100 degrees centigrade, the vapor pressure of water is only equated with the atmospheric pressure, right? So in the 100 degree centigrade temperature only the water will boils down, but that it's not true for the toluene, right? Because for toluene, in order to get the boiling get the vapor pressure equal to the atmospheric pressure, the temperature should be equal to the 110 degrees centigrade, right? So 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 for so to reach the atmospheric pressure of the to reach the vapor pressure of the toluene to the atmospheric pressure, the boiling temperature should be equal to becomes 110 degrees centigrade. But here in the statement it's saying it should be between 100 and 110 degrees centigrade, right? That means it is simply not true, right? So as discussed in statement 2, uh, the boiling temperature should boiling temperature boiling sorry, boiling T should be greater than 100 degree, but not necessarily it must be less than 110 degree, right? It simply means it's should be high enough to make the sum of the vapor pressure of water and toluene equal to the atmospheric pressure, right? But in order to make it equal to the atmospheric pressure, it doesn't simply mean it necessarily should be between 100 and 110 degrees centigrade, right? So this statement is false, basically. So in the problem, so there are two answers basically, option B and option D. So option B and option D. So basically there are two immiscible fluids. So there are different statements are given. So basically you have to think about the statements, and from that you have to conclude which of the statements is wrong. Okay, so question number 5 is done. So it's a good. So so this is it. So I hope all of you understood how all these problems are discussed, how the answers are discussed. So this is it. So thank you all of you. So let me conclude the session. So stop recording.